Hi-ho! Here we are again, Mechanical Equilibrium Part 2. Force and, be honest with you, lots of pretty dry definitions, but we got to get them down. What do you know? Well, if you had to push something, if you gave something a push, you would change its motion. Correct? And of course, if you're going to push on something, we would say you're exerting a force on it. Well, the same is true as if you pull on something. So there's our first definition of what force is. It's a push or a pull, just like our two guys down here. But we have a very special term that we like to use, the net force. Net means sum of everything, total. If you open up a box of cereal, and as you're pouring your cereal, you notice at the bottom it says net weight. It means the total weight, the weight of everything. It's everything there. Another definition for you. Like I said, lots of definitions today. They are vector quantities. We just spoke about vectors in the last PowerPoint. They're vectors. Remember, these are things that do magnitude, which means an amount, and direction, right? I can say I'm pushing to the left. All right, there's my direction. I'm pulling to the right. There's my direction. Magnitude. How much are you pulling with? A lot? A little? 1 Newton? 1,000 newtons. Little review. Another definition, support forces. A support force is exactly as it sounds, something that supports an object. One type of support force is what's called the normal force. This concrete block is pushing up, there's a direction there, pushing up to hold that polar bear in place. If it didn't push up, what do you think the polar bear would do? Well, fall to the ground. I hope you would say that. Give him some glasses here. He's a smart bear. Smarter than the average bear. Okay. So we have this thing called the normal force. These are all definitions you need to know. You're going to see them, and you're going to need to know them to be able to understand any questions we ask. Make sure you memorize these definitions. So we're going to use a spring as an example. Notice the person is pushing down with their hand on this spring, and the spring, if you can imagine this, pushing down, even if you push down on the table. So go ahead, take your hand, push down on the table, and you should feel the table, of course, pushing up on you. Those forces are equal. And that's a lecture for another day, but just take it as fact right now that those forces are in fact equal. The harder you push down on it, the harder it pushes up on you. That's a key idea. Another type of support force is tension. This lady isn't falling to the ground. Why? Something is supporting her. Not from below, but from above. And we have, it's called the tension force. And a good example of that would be a rope or a cable, something like that. If you look at our picture here, there's interactions all over the place. All right, this is pulling the sugar up, and of course the spring scale is pulling the rope up, and this is pulling the spring scale up, and all that stuff. There's lots of places we can talk about interactions between forces. Forget about my guy moving. Notice he's hanging there. There's 1,000 newtons being pulled up. You know, how much does he weigh? The force has got to be equal, and of course you can see it's 1,000 newtons. What you want to do is stop the notes right now and truly think about what's being shown here. Just don't pass it by. This is a key idea. So please, 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 please. It's a key idea. Forces are equal. Net force now, remember, the sum of the forces. We talked about vectors. We talked about what if you pull this way with, let's say, 10, and you pull the other way with 2, what's the net force? It's this little bit here, which is 8. Well, what's the net force? 1,000 up and 1,000 down. Net force is 0. 0 newtons. We have our friends, the Three Stooges again. Talk about force interactions. Of course, we're talking about on the Stooges themselves. Right here we have the Stooges pulling down. We have the scale pulling up. So put it all together, right? His weight has to equal what's being pulled up. He's got 2 ropes pulling up on him. In fact, he's in the middle. He's not off to the side. He's in the middle. So what's this one have to be? It's got to be 500 newtons. He's in the middle. So his weight is 1,000 newtons. We know this entire upward has to equal 500 because his weight is 1,000 newtons. Therefore, this side has to equal, well, 1,000 minus 170, which is 830 newtons. Again, this whole thing has to equal his weight. If he has 1,000 down, this whole thing has to be 1,000 up. There you go. So at this point, we have to introduce a new term. It's called the Equilibrium Rule. That net force equals 0. Whenever the net force equals 0, a few things can happen. We say an object is in equilibrium. We say an object is motionless, possibly, like this book. It's just sitting there. Aren't the net forces equal? Its weight up is equal to what the table is pushing. Its weight down is equal to what the table is pushing up with. But it can also be moving. Think about that. Back to our guys that were pushing that block. What happens if the guy on the right disappears? Then the block starts moving. Well, it went from 0 to some speed, let's say 60 meters per second. That's pretty fast. Think about what that means. It's changing its speed. We're not in equilibrium. But what if he hits that 60 and continues at 60? Or for that matter, put it in space. Forget about him. We get the block moving. And the block starts moving. Is there any reason for that block to stop? Is there any reason for it to speed up? No, it's moving, but it's in equilibrium. It's not changing its motion. Its motion is uniform. Is no reason to turn. It's straight line. It's only when you change the motion of an object, it's no longer in equilibrium. Back to that book. If it's just sitting there, we're not changing its motion. It's just sitting there. So equilibrium, turns out, the net forces are 0. That only happens when an object is not changing its motion. And since we're talking about forces on objects, it has to be when you have vector quantities, any type of vector quantity. Mechanical equilibrium, which is what the title of this is, we have 2 types. And all of this leads into these 2 types. Remember, we started and we talked about what net forces were, and we're getting to the equilibrium rule, and we talked about vectors before. It's all building on it. Static is exactly as it sounds. Static means you're motionless. Dynamic is the opposite. You're moving. So go back to that the previous slide, right? We can have things stationary. And of course, we can have things moving and being in equilibrium. Good example. Cat sleeping on the couch. A refrigerator sitting there. Love this picture. Love this picture. Talk about teamwork. Dynamic. Again, net force is 0. He's moving. But here's the key word right here. He's on cruise control. He's not changing his speed. He's also not going to change his direction. He's dynamic. He's moving. But he's not changing what he's doing. So what do you think? Will a person moving on a spinning ride be in dynamic equilibrium? Are these guys changing what they're doing? They might be moving the same speed, but they are changing direction. So no. So here's your key idea. Equilibrium, an object's motion cannot change. Can it be moving? Yes. Just don't change what the object is doing.